Hi guys, today I'm going to be teaching you a little bit about recursion. So recursion is a solution that breaks itself into smaller subproblems by calling itself in the function. So in this case, we see a function factorial, and in line 7, we see that it calls itself using the number n minus 1. So it's breaking the problem n into a smaller subproblem, n minus 1, and calling itself on that. For now, we won't focus too much on what this function is doing. Just know that it does make the call to itself. There are two fundamentals of recursion. These are the base cases and the recursive calls. So a base case is the stopping point of recursion. This is what tells your function when to stop recursing. So every time your function runs through, it'll reach that recursive call where it calls itself, but eventually it has to reach a point where it doesn't call itself again, and that is called your base case. It makes sure that you aren't just recursing forever. And then the second fundamental of recursion is the recursive call, and this is any call from the function to itself. So in this case of our function factorial, we see that the base case is at line 3 if n equals 0 or n equals 1, and the recursive call is in line 7 when factorial calls itself. So there can be multiple base cases, as you see here. N could equal 0 or 1, as both of those are base case, and there can be multiple recursive calls. But you always have to have at least one base case for your recursion to stop, and for a function to be recursive, it has to have at least one recursive call. So the way recursion works is by going down, recursing each time it's called, it'll call the function again until it reaches that base case, and then it'll return up and do something with that number and eventually reach back to the point where that function was originally called. So in this case, if we call main, or in main, if we call factorial with the number 5, then we see that it reaches line 7 where we return n times factorial of n minus 1. So it'll return 5 times factorial of 4. And that will call factorial of 4, which will return 4 times factorial of 3, and this will continue on until we get factorial of 1. Now we saw that our base case was if n equals 1, so that will return the number 1. 1 times 2 is 2, 2 times 3 is 6, and this will continue on until we get back to our original function call, where 5 times 24 is 120. So the answer to factorial 5 that will be returned to our function main is 120. What this looks like in memory is that every time you make a recursive call, it gets added to the stack, just like any other function call. So in this case, when factorial is called from main, it'll add that function call to the stack, and then when factorial calls itself, it'll add another function call to the stack. This continues as long as you're recursing through factorial. However, once you reach the base case and start returning out of those recursive calls, those function calls will get removed to the stack until we are back at main. So you can see after 3 recursive calls to factorial, the stack is starting to get pretty big pretty fast. There are multiple types of recursion. The first we will cover is linear recursive. This is any function that makes one recursive call. So we see in our example factorial that the only recursive call it makes is in line 7, and so that means it is linear recursive. There are no other requirements for a linear recursive solution, just that it makes only one recursive call. Then another type of recursion is called tail recursion. This also is a function that makes one recursive call, so it is a type of linear recursion, but it has the added requirement that it does no additional work after that call. So in this case, we see a function is palindrome that returns whether or not a string is a palindrome. And it has one recursive call in line 8, and that is the last thing that this function does. Our example of factorial is not tail recursive because after you return the recursive call in line 7, you still have to multiply that by line n. So the added work of the multiplication means that this function is not tail recursive. The last type of recursion we're going to cover is tree recursion. This is any function with more than one recursive call. So in this case, we have an example of Fibonacci that returns the Fibonacci number for a certain point in that sequence. And in this case, we see that at line 7 and 8, it makes a recursive call to Fibonacci n-1 and Fibonacci of n-2. So since it makes two recursive calls, this is true recursion. The reason we call it true recursion is because it splits the problem into multiple subproblems that can be represented visually as a tree where each subproblem is a branch. So in this case, I drew out a tree of Fibonacci of 5 that we'll call Fibonacci of 4 and Fibonacci of 3, and those will each form their own branches down until you get the base case that we saw is 0 or 1. And then it will start returning up and eventually give you that solution to Fibonacci of 5. You might be wondering why some of these are written recursively instead of iteratively, and it is true that most iterative solutions can be written recursively and most recursive solutions can be written iteratively. Here I showed you an example of factorial that was written with a for loop iteratively instead of with our previous example of using recursion to write it. So a reason some programmers might choose to use iteration over recursion or vice versa is to change the amount of time or space a program takes, and sometimes it's just easier to write it one way over the other. I hope you learned a lot. Thanks for watching.